This is section 7 from chapter 11, and we're going to simplify products and quotients of radicals. To simplify quotients and products of radicals, we're going to use the product property and the quotient property of square roots, along with the commutative property, associative property, and the distributive property. First problem, 3 square root of 2 times 4 square root of 18. These are basically just factors. There's a factor, there's a factor, another factor, another factor. Using the associative and commutative property, we can move these factors around in order, just like 2 times 3 times 6. That's the same thing as 6 times 3 times 2, or 2 times 6 times 3. So it makes no difference in the order because they're all multiplied together. So what we're going to do is take the numbers in front of the radicals and move them to the outside of the radical. So we have 3 times 4 here, and we have the two radicals, square root of 2, square root of 18. Multiply your 3 times 4 and you get 12. Put the 2 times 18 under the same radical and we get 36. Square root of 36 is 6. 12 times 6 is 72. Let's take a look at another one. 6 squared is 72, and we're going to do 6 squared is 72 again. We're going to do this two ways. One, and the reason to do it two ways is to show you that there's an easy way and there's a more difficult way. We're going to do the difficult way first. 6 squared is 72. 9 times 8 is 72. 9, the square root of 9, is equal to 3. That's where I got the 3. So we're going to multiply the 6 times the 3 together, right here. Now what we have left is the square root of 8. But the square root of 8 is equal to the square root of 4 times the square root of 2. The square root of 4 is equal to 2. And then, of course, we have the square root of 2 left. Multiplying everything together, 6 times 3 times 2 gives us 36 times the square root of 2. That was a long process. And the reason it was long is because we did not find the largest perfect square in 72. Let's take a look at the problem again. 6 times the square root of 72. 36 is the largest perfect square because 36 times 2 gives us 72. Square root of 36 is 6, and we have the square root of 2 left over here. 6 times 6 is 36, and we get 36 the square root of 2. So what have you learned from this example? Basically, you've learned that when you simplify, take the largest square root out of your radicand if possible, and you have a lot less steps. We're going to simplify this right here. Square root of 3 over 7 times square root of 14 over 27. We can take these two numbers, these two fractions here, and we can put them underneath the same radical. So we're going to do that right here. 3 sevenths times 14 over 27. Using canceling, this is just multiplication of fractions. 7 to 7 goes once. 7 to 14 goes 2. 3 into 3 goes once. 3 into 27 goes 9. Multiplying your numerators, 1 times 2 is 2. Multiplying your denominators, 1 times 9 is 9. We still have the radical there. So now we can separate them. Square root of 2 over the square root of 9. And it's obvious that the square root of 9 is 3. Square root of 2 is square root of 2. Sometimes we really can't do this efficiently. So we have something called rationalizing the denominator. It's the process of getting rid of a radical in the denominator and making it a rational number. That's why we call it rationalizing. Notice in this problem here we have an irrational number in the denominator. We do not want an irrational number there. We want a rational number in the denominator. So here's what we do. We take whatever this number is right here, square root of 7, and because we know about equivalent fractions, we know we can multiply the top number and the bottom number by the same number and have the same equivalent and having an equivalent fraction. Let's take a look at how that works. So our denominator is square root of 7, so that's the number we're going to use. Remember, the square root of 7 over the square root of 7 is 1, just like 3 over 3 is 1, and we can multiply any number by 1 and not really change the number. So we're going to multiply square root of 7 times the square root of 7. That's 7 square root of 7 squared. And what happens to the radical sign when you square it? It disappears. So all we have is the base, 7. I mean the radicand, 7. We're going to multiply the square root of 5 times the square root of 7 also, and we get the square root of 35, or square root of 5 times 7, which gives us the square root of 35. So that is your final answer, square root of 35 over 7. Someone once asked, can I take the 7 and divide it into 35? No, you can't. The only way you can do that is if you have radical 35 over 7, and they're both underneath the radical sign. If you had to change this to a decimal, you'd put square root of 35 in your calculator and then divide by 7. And that's about equal to 0.845. How do you know when expressions containing square roots or radicals are in simplest form? 1. No integral radicand has a perfect square factor other than 1. The square root of 9x is not in simplest form because square root of 9 you can take, which is equal to 3. No fractions are under the radical. You can't have square root of 3/4. This is not in simplest form. And no radicals are in the denominator. You can't have the square root of 3 in the denominator. So if you have any one of these cases, then your radical is not simplified yet. Here's another example. Square root of 7 over 8. This is the square root of 7 over the square root of 8 by our quotient property. Square root of 7 equals square root of 7. 8 square root of 4 over 2. Remember, try to take that largest perfect square out of there. This gives us the square root of 7 over 2 square root of 2. See that? Square root of 4 is 2. Now we have a radical in the denominator. So we're going to multiply by the square root of 2. You don't multiply by 2 square root of 2, just the radical. So square root of 2 times the square root of 2. What is the square root of 2 times the square root of 2? That's square root of 2 squared. And as we've said before, the radical and the squared cancel each other out, and you get just the 2. Of course, we had the 2 here also. And up here we had the square root of 14, because square root of 7 times 2 is square root of 14. This gives the square root of 14 over 4. And you're done. Let's take a look at this one here. A lot of arrows in here, but it's not really complicated. 3 times the square root of 8 times negative square root of 6 times 4 square root of 15. Remember we said in the first page, we take all of our numbers in front of the radicals and pull them to the outside. And right here, look at this. This is a negative. This is the same as a negative 1. That's where we got this negative 1 here. So we have 3 from here. We got the negative 1. And we got the 4 from here. So we have 3, negative 1 times 4. Multiply them together, you get negative 12. Now let's take a look at the radicals. We have 8. 8 is equal to square root of 4 times the square root of 2. Square root of 4 is 2. Square root of 2 remains. 6 over here is equal to the square root of 3 times the square root of 2. Square root of 3 squared, because we have another square root of 3 over here. That came from square root of 15. And the square root of 3 squared, of course, is these cancel out. And we have the square root of 5 left. So what do we have? We have negative 12 times the 2 is negative 24. These cancels. You have the base of 2. The square root and the square cancel. You have the base of 3. And you have square root of 15. Multiplying everything together gives us this. More examples are on page 538. I suggest you study them prior to doing the homework. Your assignment is page 538, 1 to 54 odd only. Please do the problem. Check the answers in the back of the book. If you don't get the answer, I would suggest looking at the problem again. Don't forget, you need to show the steps.